This is going to be a short video on one simple but useful fact about the order of the product of two elements. Well, we can only make a conclusion if we have an extra condition on these two elements. So we have two elements in the group. The extra condition is that they commute. And then another condition which is going to be important is that their orders, well, assuming they are finite numbers, their orders are coprime. So under these conditions we can be sure that the order of their product Fg or Gf, they are the same. The order will be the product of the orders of the factors. So this is relatively easy to prove, but the proof is at least two-stage. So we have to compute in the order of the product, we have to find the smallest power which will make it identity. Well, using commutativity condition we can rewrite this power of the product as the product of powers. And we know something about these powers, we know their cyclic behavior, they are controlled by the orders of f and g correspondingly. So again, this is possible because Fg is Gf. Then we have to see the smallest L where this is the identity. So a priori it could be that these two are separately not identities, but the product is. Let's see that this is impossible. That is the first or the second step of the proof, depending on how you count. So let's assume that, they are inverse of each other, giving us the identity, so that is the same as the negative half power. Well, we could make it even more generic, assuming that the two powers, some two powers of f and g coincide. Under this condition that the orders of f and g are coprime to each other, that should be only possible when each of these sides of the equation are separately identities. So let's see why. Well, the order of the left-hand side is a divisor of the order of f, and it is equal to the order of the right-hand side, and it is a divisor of the order of g. But these are coprime numbers, so these numbers will have to be 1. So that means that they are separately identities. Two elements with coprime orders can have equal powers if and only if these powers are just identity. So that now is equivalent to two equations that the power of f and the same power of g are both identities. And we already had a similar situation when we looked at the order of a permutation written as a product of independent cycles. So the first such L will be the least common multiple of the orders. But the orders are coprime, so this is just the product, as claimed. All the conditions are important. Both conditions which we have on our pair of elements are important. If they don't commute, we don't have any control over the order of the product. It can be anything. And if they are not coprime, again, that to some extent is true, but the statement becomes that the order of the product will be divisor of the product of orders. So that is to accommodate the situation when these two powers can be separately not identities, but the product can be still identity. So let me write that down more generally, mainly without assuming not assuming that these two orders are coprime. We only have a division statement, that the order of the product is a divisor of the product of orders. But that is useful, that is going to be used in the next video, so stay tuned.